Let us learn about the theorems related to chord and their distance from the center. Till now we have studied the theorems about angles subtended by the chord, the perpendicular drawn from the center to the chord, but now we'll be studying about the chord and the distance from the center. So the theorem 1 states that the equal chords of a circle or of congruent circles are equidistant from the center. So in order to understand this theorem, let us look at the given figure. So we have the circle and O as the center, and we have two equal chords, that is PQ and AB. So these green chords that are drawn, they are of equal length, and according to the theorem, the distance from the center, that is OM and ON, are equal. So what we can write is that according to the theorem, what we have to prove is that OM is equal to ON, and we have been given that the two chords are equal, that is AB is equal to PQ. Since we have been given that AB is equal to PQ and the distance from the center is nothing but the perpendicular drawn from the center to the chord. Now we have studied about the theorem that perpendicular drawn from the center O bisects the chord. So what we can write is that half of AB has to be equal to half of PQ as well. So the half of AB will be AM, as OM is basically bisecting the chord AB, so AM is equal to PN. Okay, so now let us proceed. We'll be drawing these two lines in order to get the triangles OMA and the triangle ONP. So what we can write is that in the given triangles OMA and triangle ONP, we have AM is equal to PN, as we have just proved, and then we have OA is equal to OP, as they are forming the radius of the circle. So we can say it that OA is equal to OP. And now since the OM drawn on the chord is basically perpendicular to the chord according to the theorem that we learned earlier, so now we have the right angle triangles who have equal length side and the hypotenuse, that is the hypotenuse are equal and the side is equal. So what we can conclude is that the triangle OMA is congruent to the triangle ONP, RHS rule. So the RHS congruency rule applies here. So now we can write that OM is equal to OP. Since the congruent sides will be equal now, so OM is equal to ON. So this is what we had to prove, and thus the theorem is derived that equal chords of a circle are equidistant from the center. Now let us move on to the theorem 2, which is quite opposite to the theorem 1. So we have the theorem 2, which states that chords equidistant from the center of a circle are equal in length. So we have the chords AB and PQ again, and it has been given this time that they are equidistant from the center, that is OM is equal to ON, and we need to prove that the two given chords will be equal, that is AB is equal to PQ is what we have to prove this time. So this is given and this is what we have to prove. So again we'll be taking the same triangles in order to prove the theorem. So in the triangles OMA and the triangle ONP, we have OM is equal to ON, that is given already, and then we have OA is equal to OP, they are forming the radius of the circle, and these triangles are right angle triangles, so we can apply the RHS congruency rule here, and since the hypotenuse and one side of the triangle is equal, so we can say that the triangle OMA is congruent to the triangle ONP by RHS rule. Thus we can say is that AM is equal to PN. and if we do twice both the side, that is twice of AM is equal to twice of PN, and we know that the line drawn from O center to the chord is perpendicular and it bisects the chord, so the twice of OM will be AB and twice of PN will be PQ. Thus AB is equal to PQ, that is the chords are equal. Thus the theorem 2 is true, that chords equidistant from the center of a circle are equal in length. Now let us do an example. So the example is, in the given figure, two equal chords AB and CD are equal, that is these two given chords, that is CD chord and AB chord, are given to be equal. When produced, meet at the point E, and we need to prove that BE is equal to DE and AE is equal to CE. Now let us draw a perpendicular from the center point O to the chords AB and CD. So the construction is, the first construction is perpendicular OM on CD, that is the chords OM, CD and AB. And the second construction that we need to do is that joining the point O to the point E. Now we have two triangles, that is triangle OME and the triangle OLE that we have just made out of the construction. Now OM is equal to OL since the chords are equal, that is AB and CD are equal, and we have drawn perpendicular. We have just proved that equal chords of a circle are equidistant from the center. Therefore, we can say that OM is equal to OL since AB is equal to CD. Now, OE is equal to OE since it is the common side of both the triangles. Now, we have two right angle triangles in which the hypotenuse are equal. The hypotenuse of one triangle is equal to hypotenuse of second triangle, and the one side of the triangle is equal to the second side of another right angle triangle. Thus we can say that the two triangles, that is triangle OME and the triangle OLE, are congruent to one another by Rss Congruence Rule. Therefore we can conclude that the corresponding side, that is ME, is equal to LE. Now ME can be split into two parts, that is MD plus DE. So ME is equal to MD plus DE, and LE is equal to LB plus BC. Now since we have drawn a perpendicular from the center and this divides the chord CD into two parts, that is CM and MD, so we can say that OM bisects the chord CD and OL bisects the chord AB. Therefore half of AB should be equal to half of CD. Thus we can write that half times AB is equal to half times CD. So the half times AB is nothing but LB and half times CD is MD. So LB is equal to MD. Thus we can cancel MD and LB since they are equal. Therefore we get that DE is equal to BE. So the first part we have just proved. Now since D is equal to B, so if we add the chord AB or CD to either of them, so if we add BE plus AB is equal to DE plus AB. Now we are adding the same thing on both the sides. Now since AB is equal to CD, since we have given that the chords are equal, so we can also equate it to DE plus CD. So we have now BE plus AB is equal to EA or AE, and DE plus CD comes out to be CE. So thus we see that it is equal.